In this paper, we present a framework for robust proximity operations using probabilistic Markov models. In many practical applications, there is need to sacrifice energy efficiency to gain better situational awareness. For example, consider a package delivery drone that uses GPS navigation for majority of its flight and relies on visual marker on the landing pad for the precision package deployment. We can command the drone to follow the energy-efficient landing trajectory, but often, due to the error in pose estimates, the UAV diverges from the ideal trajectory. This can also result in a complete miss of the target. In such scenarios, a more pragmatic approach is to deviate from the optimal trajectory at some point and acquire vision measurement for precision pose estimates. A similar approach is needed for in-space operations as well. Consider a scenario of docking of a CubeSat with a stationary target. The pose of the chaser spacecraft can be estimated using relative range measurements for the initial phase and further improved by tracking visual markers on the target. However, if reorientation is not done in time, the errors in pose estimates may result in a collision. Hence, there is need to a transition from one state to another in a robust and efficient manner. We propose the use of probabilistic Markov models to handle such transition. Various guidance modes can form a discrete state machine, and their transition probabilities can be computed based on the relative distance to the target, Mahalanobis distance of the pose estimator, and relative attitude difference between the chaser and the target. The effect of this framework can be seen from the 500 run Monte Carlo simulations. The switching using MDP results in trajectories with less docking time and impulse compared to the fixed switching distances. The framework is also validated experimentally using a couple of scenarios. For the first experiment, we use T-pods, which are 1U size motion emulators equipped with holonomic powertrain, UWB range sensors, IMU, and a camera. They are placed in the convex hull of 4 UWB anchors and commanded to dock with the stationary target. For the tuning of the estimator, we first apply a predefined set of control inputs and record the motion of the T-pods using motion capture system along with the UWB and IMU measurements. This data is processed offline to determine a set of EKF parameters.
A similar process has also been followed for offline tuning and validation of vision-based pose estimation using LED markers.
T-pods moves in the direction of the target, reorients in front of the target to acquire vision measurements, and completes the docking. Here we see a comparison of trajectories for different starting positions and orientations. In some cases where the vision measurements are available early, the algorithm decides to skip the align guidance mode and directly proceeds with the docking.